Hello everyone and welcome back to the fourth week of the second module. I hope you're doing well so far. In this week, we will see the new ways to fracture geometry. For example, how to get wood-shaped fractures or how to architect our fractures based on collisions efficiently. Also, I'll introduce you to constraint workflow between pieces. So I will start by saving this scene. As always, you can go here. I have already created this week 4 folder, and I'm gonna save it as week 4 fracture types 001. So let's save this, and let's start by creating a box. I'm gonna name it as fracture types, dive inside, and I can reshape this box by setting this to 0.5, 1, and 2. Let's raise it a little bit. Cool. So the first idea is to paint this box and use this painting to scatter some points and therefore to fracture the box using these points. So let's call a paint sub, connect it here. And if I go to the viewport, I can press enter. And if I hold shift, I can grow or shrink our brush. So let's try to paint this box. Nothing happens, and this is because we have two problems here. First one is by default the color is set to 111, and we are painting as white. So this should override this white. So in order to solve this, we have to go to the background color, apply a background color to this wall, go back to foreground color, and try to paint. And it's not working yet, and this is because this brush is painting points or primitives. But if I press W, you'll see that we don't have any points or primitive in the middle of this box. So let's add more geometry by going here, and let's change this to polygon mesh. And I can say I want, for example, 5, 20, 20. Let's go back to our paint sub. Let's set this to black. And let's select the foreground color. I go to the viewport, and now I can paint this geometry. Cool. I'm gonna drop down a scatter node, and I don't want points to be created on the whole geometry, but only on the painted one. So let's leave this as 1000, but I want the density to be driven by an attribute. And since we don't have density attribute, we have to change this to CD. Cool. Now let's jitter this a little bit with a point jitter. Only in the X direction. And we are ready to fracture this geometry using a Voronoi fracture. Here we go. Another cool trick is to Voronoi fracture this geometry using its own points. And we can get some interesting regular patterns from this. So let's add an add node, and I'm going to delete everything but the points. So we can use them to generate the cells. So let's drop down a Voronoi fracture, set the connections, and if I visualize these pieces, I'm getting this interesting brick kind of pattern. So let's explode view this, and here we go. And Another interesting trick you are about to learn before introducing constraints is how to art direct fractures. Imagine that you have a huge wall. You can copy this one, for example, 6 and 2. Let's set this to 1. So imagine you have this big wall, and you have to impact some spheres randomly on this wall. It will have no sense to add a fine fracture detail everywhere on this wall if we just want to fracture the areas around the impact. So I'm going to show you how to solve this problem. Let's make this by using this box, which is going to be our collision wall, and I want to fire some spheres on it. So let's go ahead and create a sphere. I'm gonna template the box, and I want to scatter some spheres inside the sphere. So I'm gonna move it. Let's go to top view. I'm gonna move it here. Let's make it a little bit. Okay. And let's scatter, for example, 5 points, and copy some other spheres to these points with copy to points, new spheres. Here we go. Let's shrink them a little bit. We can push them up, something like this. Okay. Now let's give them a initial velocity. But first, I would like to assemble them, to give them a name. And let's create pack geometry. So we have a name for each sphere. But let's change the prefix to balls. And now I'm going to drop down a point velocity node. I'm going to set the x velocity to positive values. For example, I'm going to start with 30, and we'll see if this fits. Perfect. Let's now create a .network, and I'm gonna plug the spheres to the first input. Remember that they should be packed and with the name attribute. And I'm gonna plug the box to the second input to use it as a static object. Okay, so let's dive inside, and let's create our rigid body nodes. I'm gonna need the solver. I'm gonna need the packed object. I can already call the spheres. They are in the first contact geometry. Need a gravity. And let's call a static object. Merge it with a ground plane. There we go. And merge all of this together. To set the static object, we can do it by using this icon here and search for the node. Or another useful way is to write an expression here that it will lead us to the path of wherever is connected to the second input or wherever input we have in this network. This expression it's called, you have to write between quotes, OP input path is this one, open parenthesis, So you have to set the level. In this case, you have to go up 2 levels. So between quotes, let's write 2 points, comma, and then you have to set the path input. In this case, is the second one. And since this goes from 0 to 3, the second one is the 1. So let's write 1, close quote, and here we go. We're not gonna use a volume representation to set this static object. So if you see, if I turn off display geometry, this will be deleted. So I need to go to the collision tabs, bullet data, and show GAT geometry. So now we are going to use a simple bullet representation of this static object because it's very simple. Also, we can change, we can even change these representations to box to make it faster. Perfect. Now let's hit play. This is not working properly because you have to inherit, if you remember, the shot velocities. I'm gonna, by the way, change this to volts. And let's set this on. So now if I press play, here we go. Let me see closer. And let me hide the wrong plane this time. Okay. Maybe we can go on with less balls. Let's say 4. Okay, let's go back. I'm gonna go frame by frame. Looks like we have a double collision here. I don't want this. Actually, let's go with 3 balls. Something like this, maybe. Let's give it a try. Wow, this goes too much. Let's try this one. Yeah, I like this. Okay, so if we're happy with these collisions, let's call them by using a dot import records. I'm gonna drop it down here, and let's set these parameters properly, dragging this .network to this first one, and writing impacts, because this is what you want. And remember, this is going to create a point for each time we have an impact. If I hit play, there, all of these are impacts. But let me show you something. If you go to the .NET geometry spreadsheet, all of these items here are objects, and therefore there is an ID assigned to all of them. You can check them. You can check it by pressing, for example, balls. And if I go here, you can see the object ID of this first object, which is 2. Ground plane has object ID of 0, and static object 1 has 1. That being said, let's jump back to SOPs. And let's see the impacts attribute we have here. For example, this one. If you remember, we only need impacts between 1 and 2. because those are the IDs assigned to the static object and the balls. So the object ID is the object ID of the spheres, and it's always 2. But what we need is, what we are interested on is the other object ID. And this will tell us whether this, let me write here object ID and other object ID, whether this RBD packed object is impacting the static object or the ground plane. So as you can see here, the other object ID is 1, which means is the static object, and here you have ground plane collisions. So basically, we have to delete everything but collisions between object ID 2 and other object ID 1. So let's simply add a blast node, and let's write parameter other object ID equals 1. Let them select it and set it to points. And here we go. We are only getting these collisions. Cool. Now we want to generate fracture points from this impact. But as you can see, they only have 1 frame of life. So we can, for example, drop down a time shift node, and let's set this to 6. Another time shift node, let's set this to 10, and so on and so forth for every collision we have. Or a procedural way is to gather all these impacts with a solver sub node. So let's create it, and it's super simple. If we merge the actual frame, let's dive inside. If we merge this, which is the input 1, actual frame, with the previous one, we are not going to lose our geometry. So let's do it with a merge node. Be sure our display is in the last node. Here, let's go back. And if I press play now, this is giving us all the impacts between spheres and the wall. Great. So let's delete this time shift. And now first I would like to have a time non-dependent node. So I'm gonna just add a time shift, and let's set this to the last frame by going here and typing $f end. Now we have a no time dependent node. If we had more impacts over the time range, they will be gathered here. So this time, I'm going to use these points to direct the fracture areas, and I'm going to use a Voronoi fracture points. So let's make it here, and we should plug the geometry to the first input, which is the box. I'm going to add the point by typing Alt and left click, and here we go. And the impact points to the second one. Let's set the display. Let's set the box as template. And if I lower the impact radius, something like this, This node allows us to scatter some points within these spheres. And it's cool because we can decide where to place points. We can place them at the surface, at the exterior or interior of these spheres. So let's go to this node, and it looks like we are not getting any points, so let's pump up the volume resolution to 100. All right, and let's start from the exterior. If I raise this value, for example 100, we're getting points outside the sphere. We can also visualize them with these visualized points. As you can see, they're getting different colors depending on where they placed. I can make them bigger by typing D to get the display options, going to geometry, and I'm going to make this point size as 8. So for now, I'm not going to use the exterior points, so I'm going to set this to 0. I can visualize the surface points. Those could be useful, so let's set this to 25. And the interior ones, maybe to 10. Okay. Let's revert our point size. And this is a multiplier. So if I set this 10 times bigger, we'll have 10 times more points. Once we are happy, we can call Voronoi fracture sub, and I can set this, I can plug this to the first input, and this points to the second one. Let's see what we get. Cool. We can start with this. So I'm gonna turn this off. And now we have the art director fracture. So let's assemble back these pieces. We don't need a name attribute because it's coming from the Voronoi fracture sub. So turn this off and turn this on. And you should save this to disk at this point, but I'm going to use a stash node instead. And this node allows us to save the geometry into the scene file. But be careful because it could increase your scene file a lot. This is just for testing purposes. So if I press stash input, now I can disconnect this and it will still working. This is not going to work on several frames. I'm going to end up this exercise testing the simulation. So we can just duplicate our .network. I'm going to drop it down here. And let's plug this fracture wall to the first input this time, and the spheres to the second one. Here they are. Let's dive inside. I'm not using a static object this time, so I can delete this node. Let's leave the balls as they were, and let's call a new RBD path object, merge it, and I'm gonna call the first contact geometry. The balls will be the second one. Here they are. Let's take a look at the collision geometry of this wall by turning this off, this on. Maybe we can ring the padding a little bit. Okay. Let's leave it like it looks now. And if I hit play, let's hit play. It looks like the whole wall is falling down at the first frames. So for this time, let's set the sleeping time to a very low value. Of course, later we're going to use the constraints to glue this piece together. So if I hit play again, let me show you by going to the wall and viewing this. I'm going to give it just one frame. Maybe it needs a even lower value here. Now this wall is inactive, and it will be like this until it gets a collision. So I'm gonna go frame by frame. And you can see we are indeed generating fractures at the impact points, which implies a very optimal way to fracture our geometry. I hope you guys can play with this a little bit more, and I guess you can get more interesting fractures from it. But for us, it's time to see how to create good fractures. And I will use the next exercise to introduce you the constraints. So we've been using this trick for a long time, and it looks like nowadays it's still working fast and efficiently. Though you can play with the automatic wood fractures the new RBD material fracture gives us. But for me, it's lower. So let's go ahead and create a few thin and long boxes. First, I will drop down a box node. Then, with the transfer node, I will set the pivot to -0.5 to start growing from the base of this box. Let's set this to 0.5. And we can play with the scale, maybe 30. Okay. And now I can set the uniform scale to 0.15. Remember, it's important to have a proper scale on your objects. Okay, so let's copy this box 4 times with a copy and transfer node to the x-axis 4 times like this. And now the trick is to shrink the object in the directions we want the fractures. Break it and recover the original transform procedurally. To do so, let's fetch a new transfer node. Let's set the y scale value to, for example, 0.5. And let's fracture these tiny pieces using a Voronoi fracture. And here, as you remember, you can either use an ISO offset node or a BDB from polygons with fuck BDB. I'm going to use this second option because it's being proved more faster. So let's add more. Resolution to these voxels, and now I can use a scatter node. Okay, let's turn this relaxed iteration off and plug this to the Voronoi fracture second input. And as you can see, we have regular Voronoi fractures here. But as soon as we transfer this back to its original position, we're gonna get wood-like fractures. Let's do it by grabbing this transfer node, actions, and create a reference copy. And I'm gonna plug this at the output of the Voronoi fracture. And I'm gonna set the invert transformations. Here we go. Now if I explode view this, I can see our pattern is being applied. Remember, you can use RBD clusters whenever you want by plugging them here, playing with these values. This time I think you need to tweak this a little bit. Something like this could work for future testings. For now, let's bypass this and let's keep working. If you look closer, maybe they still have the Voronoi pattern. So let's use our method to add a little bit of noise on it. I need to create, if you remember, an attribute called alt position and apply some noise on it, apply the fracture, and then restore the position. So let's go ahead. We need a wrangle. Let's create our attribute here. It's called vector at alt position equals position, which it's just making a copy of the position. And then I want to add some noise on it. So I'm going to use an attribute noise connected here and to the position. Let's enter the noise. And this is not going to work properly because we have very low res geometry. So we can remesh this to get more polygons. For example, 0.05. And we have to solve this round edges problem. To do so, we need a hard edges group here. So let's drop down a group node. Go to the set this to edges. I'm gonna call this group as edges. And this will work because I'm taking this exactly edges. So let's go back to the remesh node and set the hard edges to edges. Cool. Let's try to add some noise here. Maybe lower the element size. Applying some amplitude here. Maybe this should work. So let's try, break this again. And now we have to recover the original shape by using another wrangle and setting the position to the old position. Here we go. Now, after doing the transformation, we'll have more interesting patterns here. Great. Now let's end this by adding some interior detail to have our high-res geometry. I'm gonna turn off the visualization. And in this case, applying the RVD interior detail to all of them at once didn't work for me. So let's do it with using a for each node named primitive. But as you can guess, if I use this for each node, it's gonna grab every one of the pieces with the attribute name. So what we have to do is to create a new attribute for each one of these copies and do the for each using this attribute. I can do this by creating an assemble here. And this is creating a, as you know, a different value for each one of set of connected primitives. But this attribute still it still have the name. So I have to rename this attribute. Let's do it by using an attribute wrangle, for example. And I'm gonna add a new attribute called wood. And this is gonna be the name. Of course, it has to be set to primitives. So now we have the piece, the name, the name and the wood attributes. And once we fracture this again, each one of these name attributes, it will belong to the tiny pieces, and the wood will be assigned to the different boxes. So now if I go to this for each, now I change this to wood, my iterations will go as I want. Cool. So let's drop the RVD interior detail here. I can visualize the noise scale, explode, view this. And it looks like this is working properly. So let's pump up the resolution, maybe 0.05, maybe more. Okay. And you can play with this as much as you want, but I'm gonna lower down the amplitude and set this, for example, like this. Okay, that should be fine. Let's turn off this. And let's apply the same detail to every box. And here we go. Perfect. So this is going to be our high-res geometry. So let's drop down an attribute delete node to clean the attributes I don't need anymore, like alt position and this wood. No, I'm gonna leave it actually. Let's transform this by rotating 60 degrees. Assemble. We don't need to overwrite the name as usual, just to create the pack geometry. And finally, let's add an alt node and call this as alt high res geo. Cool. Now let's prepare our proxy geometry. So I'm gonna get this transform node, and I'm gonna do the same. I'm gonna create reference copy just in case we want to increase or decrease the initial rotation. And I can call convex decomposition sub. plug it here. And I first had 27,000 points, and now I have 24, so it's doing something. We will follow by deleting the attributes we don't need, like all position and segment. This has been created in the convex decomposition, but I think I don't need this attribute, so I'm going to delete it. Segment. Okay, time to assemble this. I don't want any name attribute, and pack this geometry. Let's set this to proxy geo. Now let's check if we have the same number of pieces. 1008, 1008. Perfect. I'm going to create some collision geometry. So let's create a box. Let's template our proxy geometry. I'm gonna make this thinner, larger. There you go. Okay. And I'm gonna move it. Let's place it. Let's place it here. One of them. And I want 3 of these collision boxes. So let's duplicate these 3 times and merge them together. The second one is going to be in the middle, and the third one is going to be on the top. Cool. So now I'm going to do the same. I'm not going to use BDBs as a static object. So let's drop down an assemble node. And I'm going to call it collision. Collision 0, 1, 2. Okay, so let's call a DOM network. I'm going to use the proxy geo and the collision as a static object. So let's go ahead and call the nodes you already know. Rigid body solver, RBD packed object, static object, gravity, ground plane, and let's merge all of this. Here we go. So let's first call the wood geometry. I think I'm gonna lower down a little bit the ground plane. Something like this. Let's call now the static object. As I show you, you can do it by OP input path. Go up to levels and set the second input. Maybe I can lower a little bit more the ground plane. Let's see. Something like this. Okay. Let's check the collision guide of either the wood fracture geometry and the static objects by turning off the display. I will start with the static object. Oh, no, not here, but on the bullet data. Okay. As you can see, it's being represented by a huge cube. And to solve this, you have to check this create convex hull for a set of connected primitives. Perfect. Let me see if I check box option. Now let's leave it as convex. So this is gonna work fine. And let's see the RBD packed object. I'll do the same. It looks like it should work fine as well. So let's give it a try and hit play to see our wood falling down. And here we go. Perfect. Let's now import this simulation. And I'm going to do it by plugging here a .import node. And now I'm going to use the OP input path expression here. But this time I'm going to type OP input path parentheses, and I don't need to go 2 levels up. So this time I only need 1 point. And since we are calling the first input, we have to type 0 here. Let's close this. Let's set this to fetch geometry from DOM network. And actually I can save this as a preset. So let's save this preset as import op input 0. And now if I delete this and I call another one, I can call this preset. Cool. But I don't need neither the collision geometry or the ground plane. So let's mask the RBD object, which is called RBD packed object. We can rename this as a wood. So let's write here wood. And remember that you can also fetch this as points if you have a lot of pieces. The important thing about this is the transformation matrix, which goes implicit with these points. So let's go back to the fetch geometry, and now let's call transform pieces. I want to transform this high-res geometry with this low-res one. So let's connect this properly. Let's hit the display. And if I go, for example, to this frame, here we go. High-res, low-res. And remember that if you want to render this, you have to unpack it first. So let's do it. Let's create an out wood render. Cool. We can also use our groups or attributes to colorize this. So let's throw down a couple of color subs. And in the first one, I'm going to color this by using a primitive attribute, randomize it, and this attribute is the wood attribute, the one we had created at the very beginning of this little exercise. So I can change the seed of this, and I can override the inside group of these pieces by setting this to inside and setting a new color. Remember, it's a point attribute, a primitive group. So now you can see we have a random color for the exterior, and a constant color on the interior. Okay, so far so good, but as you can see now, all pieces are falling together. All pieces are falling down, and we want to wait to make them stick together until some impact, force, or angle breaks the bonds between them. So let me first start by showing you an example to better understand the constraint types we have in Houdini. First, I created a box, I duplicate, and I merge it to have something like this. We have two simple boxes. Then I gave them a name attribute using an assemble, as you can see here. And on one hand, I packed them. And I plug it in the first input of this network. Okay, but how we can create constraints between these two pieces? A constraint is nothing but a primitive which contains three required attributes. First, each primitive, in this case a polyline because it's a line, it will have 2 points. Each point will have the name of the piece we want to constrain. So we can either connect packed or unpacked pieces, but I recommend you to use the unpacked ones because it will be more accurate. Then we need to set 2 primitives attributes, the name and the type, but we'll see this in a second. There are many ways to create these primitives, these polylines, but the most useful is using a connect adjacent pieces. So I connected this node to the first assemble. Remember the first week when I told you to split the step? Now you can see why. So if I template this, you can see this is creating polylines between these two pieces. 2, 3, 0, and 1. Those are primitives. If the pieces are too far one from another, you can tweak this value, search radius. For example, if this were 0, it can't find anything until it reaches some value. And also you can tweak the maximum number of connections for each point. And the length attribute will set the length of each polyline, and it could be useful as well. You can find this attribute here in the primitives tab. For now, they all have the same value. It's important you realize this is a digital asset. And as you can see, it automatically detects that you have a primitive name attribute here, and it does the promotion for us. 2 points. Cool. So we can finish by creating the required attributes. So inside attribute wrangle, we have to run over primitives, which means we have to run over these polylines, and we have to create 2 string attributes. The first one is going to be called string at constraint name, and this is the name you have to match with the one you set inside the dot network. We'll see this in a second. And also you have to set a constraint type. This can be all, position, or rotation. It will depend on what you want to pin. So let's see this working. I'm plugging this to the second input. Let's go inside. And this is what we add to the basic RBD sim. A constraint network that calls a set of constraint primitives. Here I'm using the second contact geometry. And this is the constraint type, which can be a glue constraint relationship, hard, or you can also use the spring constraint relationship, soft. Actually, you type constraint. You can see you have a lot of them. But for now, let's focus on these two. The glue constraint creates a link between pieces, and they will stay together until something breaks it. For example, you can see these lines are being created and inside the network, and this means that this is importing correctly the constraints. If I change this name to another one, for example, test, this will not find any constraints on the sublevel called test, and therefore he can't import anything. So let's set this as we had in the wrangle, which is called hard, and let's hit play. I want this just to fall down. As you can see, these two pieces are staying together. And this is because the impact wasn't strong enough to break this constraint. But if I lower down this value 10 times, for example, let's see what happened. As you can see, these constraints can handle this impact, and then they break. And we are breaking the 4 of them. This is why I told you that it's better to use unpacked data. Because if we had used packed primitives to create a constraint, there will only be one constraint between the centroid of each piece. But doing by this way, we can maybe just break these constraints and leave this glued together. Sometimes when we have a bunch of connections, this showing the constraints on the viewport could slow the simulation a lot. So be careful on that. Now let's take a look at the hard constraint relationship by switching this to this node. And this is useful either to pin pieces somewhere or to bend our geometry. You can see we have a different representation. We have a different guide of this. And the guide options are here in this tab, guide options. We can turn off the showing the guide geometry, the link, and if we want to scale these gizmos, we can go to hardcon rel, guide options, and tweak this radius. Maybe change the color. Let's go back to the data options. And these are the values by default. And if we hadn't override the rest length, this will try to set the distance between every constraint to this number here. The error reduction parameter is how hard the pieces will push or attract each other to reach this length in each step. And this means that these constraints are sub-step sensitive. Let's give it a first try. I'm going to press play. You can see nothing happens here, but if I go back to our connect adjacent pieces and I turn off this option to compute the length, let's go back. And now these pieces are gonna be pushed away until they reach the rest length of 1. So let's press play. And here we go. Then if I change this value to, for example, 0.1, you can see the force is weak this time. But as I say, this is sub-step depending. So if I go to the rigid body solver and change the number of sub-steps to 50, this is going to add this operation 50 times on each sub-step. And then it's going to go fast again. Here we go. Let's go back. But if I change this error reduction parameter to 0, it won't apply any force. As you can see. We don't need to see this constraint force mixing parameter for now. Cool. So let's now use them in a real scenario. I'm gonna minimize this. And I will use the proxy geo to generate the constraints. Let me organize this properly. So I'm gonna create the constraints before this geometry is packed. So let's drop down connect adjacent pieces here. Like this. As I told you, the name attribute is automatically promote to points. So let's maybe lower the radius a little bit of this. Okay. Maybe a little bit more. We want the pieces only to be affected by the nearby ones. So let's go now ahead and create our primitive wrangle to set the required attributes. The first one, if you remember, it's called constraint name. And I'm gonna start by using glue constraints and then a constraint type all. Cool. It looks like we have everything we need, the name attribute on points and the name and the type. So let's plug this into the third input. Maybe call this constraints. Let's dive inside. And we need a constraint network. Plug it here. And a constraint type. I'm going to start by using glue constraints. So I'm going to drop down this node. And as you can see, we don't have any representation of these constraints, even if I hide this. This is because the name is not as the one we had set on the primitive wrangle, and we have to call these constraints, which are in the third input, and then set the name as glue. Here we go. Let me show you these guides. And let's save this, and let's hit play. Cool. It looks like this value is big enough to prevent these pieces to be broken. So let's play with other values. Also, a way to make these pieces unbreakable is to set this strength not only to a super big number, but you can also use -1. But let's set this 10 times lower, see what happens. 10 times more. They still stick together, but they start to fall. Let's set this to 10. And here we go. Let me take a look at the geometry representation of it. As you can see, it's generating a convex hull geometry for each set of connected pieces. Maybe we can speed up this setting the representation to box. Let me see if this goes faster and it looks like realistic simulation. It looks like it goes faster, but seems to have some issues here. Let me set this to 1. Now with the convex hull, yeah, it's slightly faster. So let's use it. Now we can swap this to hard constraint. And let's change the constraint name. So I'm gonna duplicate this, and I'm gonna use this instead. This will be our glue constraints, and these are gonna be our hard constraints. Will be the same with different name, which is hard. Perfect. Let's dive inside. Let's call these hard constraints. And this is gonna slow down our simulation since we have a lot of geometry on the viewport. So let's just now that we know that this is importing the constraints properly, hide this. Okay. Let's set this by default to see what happened. Okay. As you can see, since we have a rest length attribute and the error reduction parameter is not 0, this is trying to set a distance of 1 between each set of between each piece. So let's set this to 0. Press play again. And now it's working. You have to be aware that the amount of times this constraint iteration is computed, it could highly affect the outcome. This is because at each substep, the hard constraint is trying to hold on the pieces. As you can see here, this parameter is set to -1, meaning that it's driven by the bullet solver or rigid solver constraint iteration parameter. So if I change this, let's say to 2, you will see a big difference. Let's hit play. Maybe let's pump up the gravity. And I think we are missing some constraints here, so I'm gonna pump up this value. Something like this. Let's try again. Hit play. Are we still using boxes? Yes. Okay, let's hit play. And we can increase the gravity. Let's say -150. we can start seeing our bending effect. But the geometry still stick together. I'm gonna give more pieces to this geometry by going to the scatter node, and let's pump up this to 20,000. I think this is gonna take a while, so I'm gonna pause the video. Okay, so now we have 9,000 packed fragments, so let's see what happened. I'm gonna dive inside, and let's hit play. As expected, this is taking more time to go over every frame. And it looks like it's working, but as you can see, having the rest length as 1, it allows the pieces to have a distance of 1 distance between them. We don't want that. We want the pieces to stick together. So let's set the rest length to 0, and let's hit play again. Now we should see a bending effect. Cool. So now you can see this wood geometry is bending, and as I said, it will depend on the constraint iterations and the external forces. So what we want now is to set a maximum amount of bending before breaking these constraints. So let's first go back to the scatter node. I'm gonna set this to 5,000 for the sake of the speed. Let's go back here. So how can we get these impact attributes to work over them? We need to modify some geometry attributes, so let's drop down a subsolver. Plug it into the third input of the constraint network, and dive inside. We are interested on the relation geometry. And this object merge is giving us real-time access to the constraints. So we can see how are they being affected by the external forces. If I give them several frames and I go to the tab view of the spreadsheet, let's say 5 frames, you will see a bunch of attributes. For example, the angle, the distance, force, torque, and we can work with these attributes. For example, if I set a maximum angle to break these pieces, the hard constraint will break when the pieces reach this angle. So let's drop down a primitive wrangle and let's write this statement. So let's say if the angle is greater than some value, let's create this channel. Remove prim of the first input, every prim number, and this one, it means that remove also the points. So I will leave it as it is. As you can see, every primitive is being removed, but we don't want that, so let's say, for example, 0.5. Now we are going from 31,000 to 20,000, maybe less. 0.2. Yeah, that's better. Cool, let's set this to the first frame. Let's go back. And we should see that the pieces are breaking apart when they reach some angle value. So let's hit play. And here we go. Maybe I can lower the gravity. I changed this to -90. Let's set -50. And all of these pieces have reached an angle greater than 0.2. Cool. So I would like you to play with all these primitive relationship attributes to drive a constraint simulation. And also you can create something like, I don't know, a wood fence and fire some spheres to it. And it's important that you start from scratch to get used to the constraint workflow. Later on, we'll see how to mix constraint and several methods to solve a production shock. I hope you enjoyed this week and see you in the next one. Thank you.